All right, it's kind of cool. We're starting a brand new type of math today called trigonometry. That's the title of the chapter 5, trigonometry. So we finished algebra 3 essentially, talking about exponentials and logs, and we're starting a new section called trigonometry. Trigonometry is all about angles and how we measure them, and angles usually come from things that have rotation, right? So y'all learned early on as a kid, the wheels on the bus go round and round, right? As the wheels go round and round, they travel through certain angles. As the bus goes down the road, in linear distance, the wheels are traveling through a certain angle. So there are lots of things in life that rotate. And it doesn't have to be rotation. It could be something that comes and goes at regular intervals, like the seasons, right? Or school years, right? So angles are very, very, very important. So we started studying angles way back in the day. And look at that, 190 BC, when this guy right here, this is the only known photo of Hipparchus, the only known photo of Hipparchus. But of course, photography was very, very new back then, and the photos turned out to look like drawings. But anyway, that was Hipparchus of Nicaea, and he is going to be known as the father of trigonometry. There's the word trigonometry right there. Trigonometry is made up of two words. Can y'all think of the two words here? Trigono, there you go, and metry. Metry, of course, means measure, right? We know that from like geometry. Uh-oh, it's not showing. I think there's a lag in the Wi-Fi. But trigono, it means angle, and metry, of course, means measure. This is not good. Oh, good catch, almost. Um, if I can't get this to work, what do I do here? Do you know how to make this work? Why? See how it froze? Disconnect it and reconnect it. All right. Anyway, talking about trigonometry while this is going on, uh, people started looking. The physical world was really important back then. The physical world, and so people started looking at the. Hey, that worked. Thank you. People started looking at the sky, and they used the sky to help them navigate, right? To navigate as people were exploring, right? The seas. They used the stars to help them navigate, and of course, the Earth rotates, right? So if you can measure like the angle between two stars or the same star at two different times, you can figure out or you can calculate how far you've traveled. Okay, so the word trigonometry, even though Hipparchus is known as the father of trigonometry, he's the pappy of trigonometry. The word didn't come about until another guy. Look at this name. We don't use this name much anymore today, do we? We call him maybe Bart or Bartholomew, but this guy's name was Bartholomeus Pitiscus. He was the first one to use the word trigonometry much later. So the math came first and the name of it came later. But what is an angle and how do we measure it? What is an angle? Okay, what is an angle? An angle's not a distance, right? We don't measure angles in like feet or miles or anything like that. It's not a temperature. We don't measure it in degrees Fahrenheit or degrees Celsius. So what is an angle? What does an angle measure without reading? Anyone know? What does an angle actually measure? Well, degree are the units that we measure it in, right? So that's like saying what is temperature and you say degrees Fahrenheit. Yeah, rotational distance is a good way to say it. It measures the rotation or just the rotational distance or the rotation, we just say, between two rays sharing a vertex. So if you remember from geometry, a ray has a fixed end and an indefinite end, right? And if you draw another ray at some point from that same vertex, you get something that looks like this. So you can actually measure the rotation between these two rays. And that rotation right there, typically we give a name, theta. Theta is a Greek variable that's the most commonly used variable to represent an angle. Okay. Now we have two angles here. You got to keep that in mind. You can measure the rotation between those two. And by the way, you can measure that rotation anywhere. Unlike a distance where the further out you go from the vertex, the bigger the number, an angle is the same wherever you measure it between the two rays. But you also have this other angle over here that you could also measure between the two. And of course, what do we know about the sum of those two angles? Not 180, but 360 of full rotation. We're going to talk about 360 here in just a second. Okay. So in geometry, yeah, when you first encountered trig, you measured it in degrees. Okay, and the degree symbol is this right here. So we might call this, we might say theta equals what could be a reasonable measure for that angle, the small one, theta. 40? Yeah, that's reasonable. 40 degrees. Okay, that's good. Um, I'll say 40 degrees. So we use this symbol right here. That is the unit right there. That is the unit of a degree. And for lack of a better term, I call it the degrubble, which is short for degree bubble. It's the degrubble. Hey, it's a unit. You need it there, 40 degrees. So the other one would be 320 degrees, right? The reflex angle on the outside. But anyway, we measured them in degrees, and those are the units right there. Now let's talk about 360. We know all the way around is 360. So now we can formally define what a degree is. Here's the units of measure. A degree is a unit of angular measure that's equal to 1/360th of a full rotation. 1/360th of a full rotation is now defined to be a single degree. So of course that means one rotation, if you solve, one rotation is equal to 360 degrees.
Do we use radians?
We will use radians. Yeah, we're going to get there. We're going to get to radians. Radians are actually more important than degrees for what we want to do. But we're going to start with what y'all remember from geometry. Y'all use degrees. Okay? Now, what's nice about geometry is you can take this angle right here and you can move it around and you get the exact same angle. As long as those two angles or those two rays are locked and they don't move left or right, this whole thing is the exact same angle. It can be big, it could be small, it could be pointed up, it could be pointed down. That's what you studied in Euclidean geometry. What we're going to do in pre-cal is we're going to take the angle that you had in geometry and we are going to fix it into a permanent location, and we are going to establish a y-axis and an x-axis, and we're going to start talking about x and y's. Okay, this is going to be called coordinate geometry, as opposed to Euclidean geometry. That's where we're heading. We're going to establish a coordinate system on top of these angles in a fixed standardized method. Okay, so let's talk about 360 for a second here. It's defined to be 1/360th of a rotation, a single degree is. But 360 seems kind of like an arbitrary number, right? You would think in today's age, maybe we would say one rotation is equal to 100 degrees, right? That's kind of the metric system. Wouldn't that be good if a rotation were 100 degrees? So back in the day when they established 360 degrees for a full rotation, why do you think they chose 360? Any guesses? It seems kind of an arbitrary number, doesn't it? I know if you were at the first meeting and you were trying to establish, hey, once all the way around, how many degrees do you want to make that? Do you think you would have just raised your hand and said, how about 360? Or maybe you would have raised your hand and said, I say 100 degrees. Let's vote. Who would vote for 100? Who would vote for 360? I would probably vote for 100, wouldn't you? Yeah, because it's decimal, right? It's a power of 10. It's 10 squared. We're comfortable with 10. And if we had to divide 10 into 4 parts on the coordinate plane, each quadrant could be 25 degrees. That would be nice, wouldn't it? 25, 25, 25, 25. It's like 4 quarters equals $1. Who votes for 100 degrees? Who votes for 360? I vote for 100, but they didn't. They didn't. They voted for 360. Why?
More precision.
More precision? Yeah, that's kind of getting into it. If you had to divide each quadrant of 25 degrees into parts, 25 is not an even number, right? So even if you divide it in half, now you have decimals, right? So you can get as precise as you want, but the numbers aren't as pretty, right? So that's one of the reasons 360 was chosen. 360 has lots of integer factors. It has lots of integer factors. Okay, so when you split 360 up into 4 parts, you get 90, and then 90 is an even number. So it has lots of integer factors. We can start listing them. 1, 2, 3, 4, 5, 6. Okay, the first 6 integers are factors of 360. That's one of the reasons they went with 360 over 100. The number's bigger and has lots of nice integer factors, so you can split it up without having to use fractions as many times. But there's a more important reason, okay? Remember that I talked about a rotation, things that come around full circle. And I already mentioned it in class today. These people were trying to plant crops so that they can live, right? And what happens when you're planting crops and trying to work the earth, right? What happens every so often to the temperatures? They, they change, don't they? What? Yeah, 1 year. There you go. 1 year is how many days? We know it's 365.25 something, right? This is a leap year, by the way. 2024 is leap year. So we get an extra day of February. Hooray. But yeah, it just so happened that every 360 days or so, the seasons started repeating, right? Now, they didn't know it was 365.25 back in the day. And even if they did, I doubt they would have chosen one rotation to be 365.25, right? Because it's not a sexy number. It doesn't have a lot of nice integer factors. Whereas 360, which is close enough to 365, does. So that's kind of one of the main reasons. The ancient Babylonians had a big part of it. The ancient Babylonians didn't use a base 10 number system. The ancient Babylonians who studied angles and angle measure had a base 60 number system. Can you imagine that? A base 60? We use base 10 because we have 10 fingers, right? 5 on each hand. Why do you think the ancient Babylonians used base 60? What's that? 60 fingers? Yeah, the ancient Babylonians had 60 fingers. That's exactly right. Very good. Yeah. Now, I'm just making that up, and you're just making that up, but it sounds reasonable, right? Have you ever seen an ancient Babylonian? No, but if you did, they'd probably have 30 fingers on one hand and 30 on the other. Or maybe they were wacky. Maybe they had 20 on one hand and 40 on the other. But it made it easier for them to count, base 60. Yeah, so the base 60 number system is called the sexagesimal system. Sexagesimal. Yeah, that's right. The first three letters are sex. Sex. Okay? So that's why 360, which has a lot of integer factors, is sometimes called a sexy number. Okay? It's a sexy number, right? 60 is definitely a factor of 360, and it's a sexy number that is close enough to once around the sun, right? 1 year. So that's kind of why people believe that they use 60. Now, they didn't really use decimals back in the day when they looked at parts of a degree. Okay, we have 1 degree is the 360th of a rotation, but we also have parts of degrees. So here's what they came up with as well. They came up with parts of degrees to be not decimals, but something else. And it's we still believe in the base 60 number system every day when we live our lives. There's still a remnant of the ancient Babylonians base 60 number system. Can you think of where in our life we use base 60 or 60 is such a prominent number? Time, clock. Yeah, the clock. Very good. 1 hour is how many minutes? 60 minutes. And 1 minute is how many seconds? 60. Okay. That's a vestige of the sexagesimal number system from the ancient Babylonians. Well, it turns out that they did the same thing. They did the same thing. They didn't measure in decimal degrees. They measured parts of a full degree in what's called minutes and seconds. Okay, so 1 degree is equal to 60 minutes. Their degree was kind of like our hour, if you want to think of it in terms of time. Their full degree was similar to our hour. 1 degree was 60 minutes. We have units now. We can write 1 degree equals 60 minutes. We use a single hash mark as a minute unit. And then, of course, just like what we have, 1 minute is equal to 60 seconds. And we write that like this. 1 minute, oops, I used the degree. 1 minute is equal to 60 seconds. So just keep that in mind that when we talk about parts of degrees or parts of minutes and we use seconds, we're not talking about time. We're talking about parts of full degrees. Okay. Now, this way to measure degrees, parts of degrees, is called DMS. DMS is short for, guess what? Degrees, minutes, seconds. Okay. And we use degrees, minutes, seconds every day as well. You might encounter degrees, minutes, seconds every single day. Do y'all come into contact with it ever? Do y'all know where you come into contact with it? Where do you come? Well, not time minutes, but do you ever come into contact with minutes and seconds when you're talking about navigation? Yeah. Have you ever looked up the coordinates, the GPS coordinates or something? GPS coordinates are latitude by longitude. And guess how they measure latitude? In degrees, minutes, seconds. And guess how they measure longitude? In degrees, minutes, seconds. Yeah, you may see something like 28 degrees. Here's an example: 28 degrees, 15 minutes, 32 seconds. Okay. You ever seen something written like that? Yeah. Those are the coordinates. Those are the latitudinal coordinates of something on Earth. Okay. So what that means, what would 28, 15, 32 mean? It means if you take planet Earth and you look at it like this kind of model, your latitude is the first number. So imagine in the center of the Earth, you have a line going straight across to the equator. This might be 28, 15, 32 north. Okay. What that means is you rotate up about 28 degrees, boom. And when you hit the surface of the Earth, you're going to hit this latitudinal line, sometimes called a parallel. So somewhere along that 28th parallel, you can have a point. Now, to pinpoint a point on that parallel, you use the longitudinal coordinate, which gets you to rotate to somewhere along that parallel. And where those two intersect, you have your coordinate on Earth. So it's a nice way to navigate through a three-dimensional spherical space. Okay, so we still use 60. We still use degrees, minutes, seconds. We're going to be primarily interested later with something called radian and decimals rather than degrees and minutes, seconds. But we're going to walk through the path of degrees, minutes, seconds, and I'm going to insist that you know how to use them and to convert back and forth between the two. Okay? And I'll show you how to do it right here on example one. All right, so what is an angle and what does it measure? An angle measures rotation. The units that we use are degrees. And there's two ways to do it: decimal degrees, which is pretty conventional, or degrees, minutes, seconds, which I'm going to teach you how to use right now. Oh, by the way, I want to retreat back up here. There's one more thing I wanted to say. In geometry, you probably referred to angles using the 3-point nomenclature. Like you would have A, B, and C, and you would have angle ABC, and then you'd have the measure of angle ABC. Okay? We're not going to use that anymore, although it still works. We're going to label the angle as some variable like theta, and theta is going to represent not just the name of the angle, like angle ABC, but it's also going to represent the measure of the angle, like 40 degrees. We use them interchangeably. Okay? So it's a little bit easier, a little more straightforward. Okay, let's try this out. Draw an angle of 76.425 degrees and then convert it to DMS. All right, so let's do that. 76.425 degrees. What I would kind of tell you to do is to get in the habit of drawing your initial ray. This is what we call this, an initial ray. Try to draw it facing due east, okay? Because when we start putting a coordinate plane on top of this, our angle that we start with is always going to be on the positive x-axis. Okay, so draw it going due east. And then rotate 76 degrees. 76 degrees should be a little bit more than, we know this is 45, right? Halfway through is 45. And we know straight up is a right angle, which is 90. So that's what we use for comparison, isn't it? So I know it's going to be somewhere between 45 and 90, so I'm going to draw it about right here, somewhere in there. And then I'm going to label this as theta, and then I'm going to come over here and say theta is 76.425 degrees. So what that does is it allows me to name the angle instead of angle ABC, and it also allows me to talk about its measure, 76.425. Now that's in decimal degrees. This is decimal degrees, which means at 76 full degrees plus not quite another half of a degree. I want to convert the part that is left over, 4.425, I want to convert that into minutes and seconds. Just like if we had a part of an hour, we would measure it in minutes, wouldn't we? Okay, let's do that. So here's what we're going to do. We're going to take the decimal part, 0.425, and that's going to be in degrees. and we're going to multiply it by the number that will allow us to convert it to minutes. Now, I want to get you used to stoichiometry. Oh gosh, I know. It's going to be easier stoichiometry than in your chemistry class. Uh, but it's basically looking at factors equivalent to one. So this is also called dimensional analysis. If you don't like stoichiometry, you can call it dimensional analysis. I have degrees, and you can put it over one. So I have degrees in the numerator. I want degrees to divide out, so I'm going to put my degree bubble on the bottom, and I want minutes to appear, so I'm going to put minutes in the top. Now we know that 1 degree is 60 minutes. We know that, okay? But notice what I can do. I can write these called scale factors. These are scale factors that are going to be equal to 1. I know that 1 degree is the same as 60 minutes, or 60 minutes is the same as 1 degree. Those are fractions that are equivalent to 1. They don't equal 1. 1 divided by 60 is not 1. But 1 degree is 60 minutes. So when you include units, you get these scale factors that are equivalent to 1. And isn't it okay to multiply by 1? It doesn't change the value. So that's why we set up the units first. We want the units that we don't want to divide out, so that's from high to low, and the units that we want to have in the final answer need to emerge. So now we just fill in. How many minutes in a degree? 60. So this is going to be 60 over 1. 60 over 1. And if you notice, the degrees bubbles divide out. I like to make the sound and I like to divide them out. And now all we got to do is multiply those together. Now, here's where your calculator can be helpful. So everybody, you can go grab one in the front, or let's use the Minnesota calculator. Dun, 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 Minnesota calculator. Oops, that wasn't it. We'll be using the calculator here, so if you want to grab one, you can. They're up there in the front. All right, so we finally got it here. So now we just type it in, 0.425 times 60, and we get 25.5. And the units now are minutes. So we got 25 full minutes plus zero point 0.5 of another minute. Well, we have a decimal part left over again, don't we? So now what I want to do is I want to take the decimal part, 0.5 minutes, and I want to convert it down to the next smaller unit, which is of course seconds. Now, we probably could do this in our head, right? 0.5 is a half. A half of a minute is how many seconds? 30. Now, it's the same with time as it is with angles. But let's go ahead and go through the process of the dimensional analysis. I have minutes in the top, so I want minutes to divide out, and I want seconds to appear. Well, this is going to be 60 over 1 or 1 over 60 again, right? 1 minute is 60 seconds. So we know we have the conversion factors 1 minute over 60 seconds or 60 seconds over 1 minute. We can use either one of those. We want the 60 seconds over 1 minute. And now you see that your minutes divide out. And if you do the math, you could say 0.5 times 60. And of course, we get the answer that we were expecting. We get 30 seconds. So here's the conclusion now. So we know that 76.425 decimal degrees is equal to 76 full degrees plus 25 full minutes plus 30 full seconds. We write it without the plus signs there. It's a stylized way to write it. It's really 76 plus 25 plus 30, but like with a mixed number when you were growing up, we get rid of the plus sign. So 76, 25, 30. They mean the exact same thing. Now, for us, there's no smaller unit than seconds, so if you had a decimal at this point on the seconds, you would just put decimal seconds to 3 decimal places. So like 30.625, whatever, seconds. Just like on the time on the clock, we really don't go smaller than seconds, right? We don't ever measure something usually in like nanoseconds or whatever. Tenth of a seconds maybe on a shot clock or something. Those two are exactly the same. Which one would we see more often? It depends what profession we're in, right? If we're a sailor or a navigator or we work for a GPS company who constantly recalibrates these things to make sure everything is good. Degrees, minutes, seconds are our lives, right? That's what we use. Okay, let's look at a nice little application of this. New Braunfels, Texas. If you look it up on Wikipedia, you can actually look up where New Braunfels, Texas lives. Bless you. The coordinates for New Braunfels, Texas are 294210 north by 98.727 west. Now that pinpoints a specific place in New Braunfels, Texas. I don't know exactly where it is. It's somewhere on the plaza. If you ever try to Google that it shows up somewhere on the plaza by the NBU building, the old NBU building. I think it's trying to pinpoint it directly where the plaza is, but it's a little bit off. Okay. I used to think it was like the mayor's house, like in the mayor's living room, right? But that was not because the mayor changes. So let's see what that looks like again. If we look at planet Earth, let's see if we can figure out where New Braunfels lives. This is your North Pole and South Pole. Okay, this is the North Pole. This is the South Pole. And those are going to be your longitudinal lines. And then you have your equator, which looks something like this. Okay, this is the equator. The way that these coordinates work again is from the center of the Earth, you imagine a line going straight out to the east on the equator, and we rotate up 29 degrees. Okay, somewhere in there. Boom, and we hit the surface of the Earth. That's 294210. So we rotate up 294210, and we hit this right here. This will be like the 29th parallel, if you will. Now, somewhere along that latitudinal line, New Braunfels lives. So how do we navigate? Well, we also start here from the North Pole, South Pole. There is a starting place called the prime meridian. Okay, and from the prime meridian, we rotate. We rotated north to go up instead of down. From the prime meridian now, we rotate 98 degrees west. So we're going to rotate a little past 90 degrees, and we're going to come around back right there. Okay, that's a little bit past. Now your longitudinal lines are the same size as you rotate that great circle that runs to the North and South Pole. Just imagine spinning it around. Every single circle that you make is the same size, whereas the parallels are like slicing a tomato. They get smaller as you go up. So New Braunfels lives somewhere right there, around the corner. Okay, that's where we live. Now, I want to figure out what those are in uh, decimals. So I'll do the first one with you. Let's convert 29:42:10 to decimals. So 29 degrees, 42 minutes, 10 seconds. And you can do the other one. So we're going to take the 42. This one's a little bit different. When we're converting the other way, we're not kind of doing it in the sequence, right? When we have start with decimal, we're doing it in sequence. We're taking the fractional part, we're converting it, and if there's a fractional part left over, we're converting it. When we're going the other way from DMS back to decimal, we already have two fractional parts. We want to convert those back to full degrees. So here's what we're going to do. We're just going to write it as a single equation. 29:42:10 is equal to 29 full degrees plus 42 minutes over 1. Now we're going to convert the minutes right there in the problem. We got minutes in the problem bottom. We want degrees in the top. So that's going to be 1 degree is 60 minutes. So we're essentially dividing by 60. When we converted from decimal to DMS, we multiplied by 60. You can see here that we're dividing by 60. Thank you. All right. And then we go ahead and say plus. Now we got 10 seconds over 1. Well, now we got to convert back from seconds to degrees. How do we convert back from seconds to degrees? Well, we should probably go through minutes, shouldn't we? So I'm going to have seconds down here and minutes up here. So we're going to have 1 minute is 60 seconds. And if you notice, dimensional analysis will tell you that your seconds divide out. And now I'm left with minutes. So now I multiply by, I need minutes to divide out. I want degrees to appear. So 1 degree is 60 minutes. All right. And now we've laid out the equation. Notice I'm dividing by 60 twice, which is essentially what we're doing. Or you can go straight from minutes to seconds, or from hours to seconds, right? Hours is how many seconds in an hour? 60 squared, right? Yeah, 3,600. So if you want to go straight from seconds to degrees by dividing through by 3,600, you can, or you can divide by 60 twice. But here we have the equation laid out. It's not doing it in sequence. We have two parts, and we're converting both of them to degrees in the same equation. Now we just type this into the calculator. And you don't put units on your calculator because the units are already taken care of. So you go 29 plus 42 divided by 60 plus 10 divided by 60 divided by 60. We just literally divide by 60 twice. We're literally just typing in what we have on our paper. We don't have to worry about the ones, do we? Because dividing by 1 and multiplying by 1 doesn't change anything. All right, so does that look good? 29 plus 42 divided by 60 plus 10 divided by 60 twice, divided by 60 divided by 60. We hit enter, and we get 29.702 decimal degrees or 29.703 decimal degrees. We round or truncate to 3 decimals. Now, which one do we probably have a better intuitive feel for? DMS or decimal degrees? Do you understand DMS? Like if I say 29.4210, you kind of have an idea of how much to rotate past 29? I don't. I sure don't. I don't have a lot of experience with DMS in terms of rotation. But if you tell me 29.703, I know to go 29 full degrees plus another 70% of a full rotation, right? We have a better understanding of decimal degrees. Unless you work with DMS on a regular basis, you probably don't have a true appreciation of how much extra to rotate past the full degree. So DMS exists, and I want you to understand how to use DMS, but eventually we're going to shift to decimal radians, not even degrees. Okay, so there's two examples. Converting once from decimal degrees to DMS, we do it in sequence, right? We take the part times 60, the part times 60. When we're going back from DMS to decimals, we do it in one fell swoop. All right. Go ahead and do the next one on your own. Do the next one on your own. Do 98 degrees, 7 minutes, 27 seconds. Convert it on your own. I'm going to convert mine on my own, and you can compare your answer to mine. There you go.
So if 4210 is giving like 7, would there be a scenario where you get like where it spills over to 29?
No, it wouldn't. No, because that's like if you're using your minutes correctly, it won't spill over, right? Like we don't unless we said like 65 minutes, that's an hour and 5 minutes, right? We stop at 60. So anything that's over 60 goes up to the hour mark. So it'll never spill over. That's a good question. We could talk about 65 minutes in time, but we don't talk about 65 minutes for angles. Good question. Bless you. Bless you. When we quiz over this, I will expect to see your full worked out conversions right there. So this line right here, you will get a check for each of those terms. You'll get a check for keeping the 98. You'll get a check for that conversion, and you'll get a check for that conversion. Now, notice what I did on that third conversion. Instead of converting it twice from minutes to seconds and then seconds to degrees, I went ahead and did 27 divided by 3,600. That's pretty common. So if you just want to say 1 degree is 3,600 seconds, like 1 hour is 3,600 seconds, you could do it in a single calculation instead of dividing by 60 twice. But either way, you get 98.124 when you round, and you get degrees. Now, in the past, I've told y'all if y'all want to, at this point, if you want, you can legally take your cell phones out and you can text your parents the coordinates of New Braunfels, Texas. So here's what happened one year in 2013. Hey, mom, New Braunfels coordinates are this. And then the mom goes, okay. I just wanted to tell you because why? I love you, right? I love you too, sweetheart. See, that was nice. You're sharing these coordinates with your parents. Here's what happened another time with Mama Bear. Hey, New Braunfels coordinates are this, and they showed up as hyperlinks. And Mom said, "Okay, I just thought you should know because I care about you." See, so if you would like to at this point right now, if you want to take out your phone and you want to text your parents what the decimal coordinates are of New Braunfels, Texas, here they are. It's 29, right? You can say, "Mom, the coordinates are." Oh, I'm frozen over here now. No, I was charging it this morning, but that's 29. Yeah, my finger's not even working. Anyway, you could say it's 29703 by north by 98.124 west. Okay. And if you get a nice reply, you can email me a screenshot of the reply, and I'll squeeze it in here for posterity, so we can look at the reactions from your loved ones. Okay, like we've done here. No one wants to do that. No one loves their parents that much. Okay, that's up to you. All right, we got 9 minutes left. So let's see if my pencil works now. Oh, yeah, now it works. It just needed a little extra attention. All right, so remember I said up here that these angles that we draw, if you rotate them around like this, oops, it's if you rotate them around, it's the same angle whether it's big or small, however it's rotated. As long as the measure between those rays stays fixed, we've got ourselves the same angle. But in this class, we're going to standardize it. We're going to put a coordinate system on top of it, and then we can start assigning x and y values. So here's the definition of an angle in what's called standard position. An angle in standard position has its initial ray on the positive x-axis and something that's called the terminal ray, that's where it ends. It may land anywhere in the coordinate plane. A counterclockwise rotation is going to result in a positive angle, and a clockwise rotation is going to be a negative angle. And then we use Greek letters. This is alpha, phi, or I'm sorry, theta, phi, alpha, and beta. We typically use Greek letters to denote both the name and the size of the angle, as I already mentioned. Here are some examples right here. Standard form. Notice the x and y axis. The initial ray is this right here. It's always the positive x-axis, so we don't even need to draw it. This is the initial ray, which you don't even need to draw. You don't need to draw because it's always the positive x-axis facing due east. Okay, you don't need to draw it. And then if you rotate up here, you're landing somewhere mid between. This could be like 45 degrees, right? And is this positive or negative? Positive. Okay, so counterclockwise is going to denote a positive angle. So this would be a positive angle. Let's call it theta, and then let's go ahead and say approximately theta. What could theta be here? Let's just approximate it. Yeah, it looks like it's right in between 0 and 90, so that could be a 45-degree angle. Perfect. Now, what's nice about all the way around being 360 is when we divide it into 4 quadrants, rotating counterclockwise, we call that quadrant 1, we call that quadrant 2, we call that quadrant 3, and we call this quadrant 4. So if you ever wonder why they're numbered in that fashion, it's because of the definition of an angle in standard form. Counterclockwise is considered the positive rotation. Now we can also partition the quadrants up into degrees. We know this would be 90 degrees, right? What would the next measure be? That's 180. That's halfway around. What would 3/4 of the way around be? 270. Very good. 180 plus 90. And of course, this is 0 degrees if we don't go anywhere, but it's also, if we go all the way around, it's 360 degrees. We call these two angles what? Do you know? They're not the same angle, are they? But they land at the same place? These are called co-terminal angles. They land at the same place. They land at the same place, which means they share a terminal ray. They share a terminal ray. And we can keep going if we wanted, right? Some of the skateboard tricks now are more than 360. People are spinning like I saw Michelle Kim or whatever the female skateboarder that is. She's like a 12. She's like a 1280 or something on the half pipe. That's like my SAT score. Goodness gracious. Um, so we can measure more. Like if we wanted to keep going past 360, the next quadrant would be 450, so on and so forth. All right, let's look at this one here. Let's call this angle theta. We could actually go clockwise, right? So would theta here be positive or negative? Negative, okay? Clockwise is going to equal the negative position. And so this would be negative 90. This would be negative 180. This would be negative 270. Oh, by the way, don't forget your degrebles. This is one of the things that I don't like about having to use degrees. We always have to put our units on it or we're going to lose points. It's a unit, okay? And if you don't put units, that's something else later called a radian, which is why we need to reinforce using the degrebel now. So what would be a possible angle measure for this one? Very good. I like that. Negative 225 degrees. Because it looks like it's another 45 past negative 180, right? So 180 plus 45 is 225. Very good. And it's still negative because we're rotating clockwise. Now, did you ever have negative angles in geometry? No way. A negative angle in geometry didn't make sense because you were talking about measurable angles inside geometric shapes, right? So only positive angles made sense. But now these are actually vectors, aren't they? They have a sign, positive and negative, and they have a magnitude, okay? This is a vector quantity. We can now have negative angles. They have position, or I can just say they have direction and they have a magnitude. They're vectors, okay? Direction and magnitude. All right, let's take a look at this fellow over here. Is this going to be a positive or negative angle? It's a positive because we're rotating counterclockwise. And it looks like we go all the way around, right? All the way around plus another 45. So that should be like a 360 degree plus another 45 degrees, which will end up being what? That's 405 degrees. Did you ever have an angle in geometry that was ever bigger than 180? No, much less 360, much less 405 degrees. If you had an angle that was bigger than 180 in geometric shape, I guess you could. I can think of a structure where the angle is bigger than 180, but you can have an angle bigger than 360, not in an inside shape. But here we can. We can go past 360. All right, last one here. Let's do this one. This should be a positive or negative angle? Positive, so let's call it theta. And theta is going to equal, we go all the way around to 360, plus another 180, right? Plus another 180, plus another 45. So that gives us what? 585. Woo! It's getting hot in here, right? 585 degrees. All right, so that's where we have to stop for today. But you get the idea, right? An angle measures rotation. An angle in standard position is a vector. It has direction. It has magnitude. And we're going to start assigning x and y's to this stuff soon enough. And then we start talking about equations. It's just we've opened Pandora's box when it comes to the world of trigonometry.